So number 46, the formal charge of xenon in XeF4. So they give you XeF4, and to find formal charge, remember that's equal to the number of electrons assigned to it on the periodic table. For xenon, that's 8 because it's in group 18, minus the number of electrons assigned in the Lewis dot structure, remembering that there's only one assigned per bond, because for a bond we assume one goes to one atom and one electron goes to the other. And so for xenon, we'd have 1, 2, 3, 4 from the bonds, 5, 6, 7, 8 coming from the unshared pairs of electrons. So 8 minus 8 is 0, so the formal charge on xenon is 0. The oxidation number of sulfur in SF6, so this really doesn't have to do with the Lewis dot structure, it has to do with assigning oxidation numbers on the periodic table, and we know that fluorine's always -1. It's the most electronegative atom on the periodic table, so fluorine is -1. Whatever sulfur is plus -6 has to add up and equal to 0, and so something plus -6 equals 0, that means sulfur is equal to +6 for its formal charge. 48, what is the molecular geometry of XeF4? So you look at your little reference chart right here, and you find out that we have 1, 2, 3, 4, 5, 6 total electron domains. So the electron domain geometry would be the family of 6 right here, the octahedral family. That's called the electron domain geometry. It's actually what is the molecular geometry for this. And so over here are the molecular geometries then based on how many shared and lone pair electrons there are, shared and unshared pairs. This one has 1, 2, 3, 4 shared pairs and 2 lone pairs. So 4 shared pairs and 2 lone pairs would be square planar 90-degree angle. So square planar, and then of course 90 degrees if they asked you for the bond angle. Number 49, what are the bond angles in NO2 minus 1? So NO2 minus 1 right here would be 1, 2, 3 domains of electrons. So the electron domain geometry would come from the trigonal planar area. This happens to have 1, 2 areas of shared and 1 unshared. So 2 areas of shared and 1 unshared, that would be bent right here. So the name for this one would be bent. And the bond angle, it says approximately 120. It would be a little bit less though, because these unshared pairs would actually squish it together a little bit, and so you'd probably guess like 116 degrees, but less than 120 is absolutely fine. Number 50, what is the electron domain geometry? So the electron domain geometry now is these guys right here, the family that it comes from. And you get this sheet on the test, so read the words right there carefully. In XeF4, so we have 1, 2, 3, 4, 5, 6 domains, and that would be the octahedral family. So octahedral. And then what is the molecular geometry? That's what it asks for the next couple. The molecular geometry in N2O. So N2O right here. Look around the central atom right here. Notice we have 1 domain right here and 1 domain right here. So 2 domains of electrons. 2 domains. The only choice is linear right there. And what is the molecular geometry in SF6? So SF6 has 1, 2, 3, 4, 5, 6. 6 bonded, 0 non-bonded, octahedral. Of the molecules pictured, which are polar. So polar molecules now mean that you have an uneven distribution of charge, and so you look for asymmetry. And remember, you have to look in 3 dimensions for this, so be careful when you're looking at them. This, of course, would be perfectly symmetrical because you slice it any single way, it's going to be the same, so this would be nonpolar. This one, same thing. Slice it any one of the 3 ways, you end up being nonpolar. This guy, well, this is tricky. You can say if I sliced it this way, it would be nonpolar. If I sliced it this way, it would be nonpolar. But if I do it this way, it would probably end up being polar, because I'd end up with 2 fragments that would be uneven distribution for one another. This guy right here, if you look at this screenshot of it, I'm sorry, this kind of three-dimensional, you could slice it this way, you could slice it this way, and you could slice it this way, and it would end up being the same every single direction. So this one is non-polar. This one obviously is polar, because if you slice it here, you get two different things. This one, well, this one's tricky because it has this unshared pair of electrons on it. Normally you'd say, well, if I'd slice it right here, it'd be the same on both sides. But remember, if you sliced it this way, you'd have an unshared pair on one side and oxygen on the other, so this one would be polar. Always remember those unshared pairs of electrons are part of the slicing in half. And if you put it on one unshared pair on one side and the shared pair for the oxygen on the other, it would obviously be asymmetrical. So we have two polar molecules in there. I'm sorry, three. Polar, this one's polar as well. Let's see, for C2H2Cl2 molecule pictured, which of the following is true? More than one possible answer. Let's see, the molecule is planar because of the pi bond. That is true. So, if you look at this shape around this carbon or around this carbon, you have 1, 2, 3 bonded, 0 non-bonded. So that would be trigonal planar. So that's how you know it's planar, because there's 3 bonded domains around either one of them. The molecule can rotate freely about the double bond. This is not true. Now this comes down to something about sigma and pi bonds, and you know that one of these is a sigma bond, the other one is a pi bond, and a sigma bond of course means that it's a head-to-head orbital overlap between the carbons. The pi bond means that it takes these unhybridized p orbitals and it actually overlaps over the top and the bottom like this, and this offers some stability that doesn't allow those carbons to rotate at all. And so B would not be true. There's another isomer in which the chlorine atoms are on the same side of the double bond. That is true. So you could move this chlorine down here, and you can move this hydrogen up here. This particular isomer is called a trans isomer because the, TRANS, because the chlorines are transverse of one another. If you put the chlorines on the same side, where the chlorine would be here and the hydrogen would be up here, it's called a cis version of that isomer. You don't need to know the names, just know that there's two different versions. The geometry around each carbon atom is trigonal planar, and that we already identified as 1, 2, 3 domains around each one.